Okay, you can see my screen?
Yes.
Okay, I'm going to probably go, because I have multiple screens, I'm just going to go real quick through this. So good morning and good afternoon. Welcome to the AGI-ESIC webinar. I will, today we're going to have 4 speakers share about a project. So just a little bit about AGI for anybody that's new to the seminar series. AGI is a collaboration between P&L and WSU, and we're really working to work together to help advance as we look at the advanced grid modeling and support that, as well as look at the workforce of tomorrow, and particularly in the North American power grid. Here's a link here if you're interested in learning more. We have recently done our strategic plan, and you can get more information on that on our website. And we just this morning, our fall newsletter hit your inbox, hopefully. If not, you can, I'll put the link in the chat and you can see that, as well as you're welcome to go to our website and sign up for that to learn more about that. A couple interesting set of resources. We do have some, we had AGI Industry Day, and for that we actually had an opportunity to have 9 speed talks by industry across the Pacific Northwest, and can give you some great perspectives there to learn more. And we also have these seminars, and videos of these seminars are available. And this is our seminar we'll have today. So with that, I would like to introduce our colleagues here that will be presenting, which is called the GridSandbox Automated Workflow Management for End-to-End Grid Analytics. And we have 4 speakers. We have Srivastava, who wears multiple hats. He's part of the ESIC at WSU, but is also the chair of Computer Science and Electrical Engineering Department at West Virginia. He is an adjunct faculty member at WSU and a senior scientist at P&L, and he's currently serving in the Raymond J. Lane as a Raymond J. Lane professor and chair at West Virginia University. He received his PhD from Illinois Institute of Technology in 2005, and his research interests encompass data-driven algorithms in power system operations and control, including resiliency analysis. He went on sabbatical to a bunch of different places across the US and the world, and is very involved. He's chair of the IEEE Power and Energy Society Peak Committee, as well as other technical committees across IEEE PES. Additional information on his bio is available in the flyer. Dr. Henry Huang is a laboratory fellow at P&L, as well as a research professor at WSU. He served as a technical advisor at the U.S. Department of Energy EERE Solar Energy Technologies Office from 2019 to 2020. His research focuses on advancing analytical methods for understanding and managing the emerging complexity in the power grid with the new mix of generation and consumption. He has over 190 peer-reviewed publications in the area and is a fellow of IEEE. He's also active in the IEEE PES technical areas. He received the 2008 P&L Ronald Brodzinski's Award for Early Career Achievement and the 2009 Outstanding Young Engineering Early Career Award from IEEE PES. Our next speaker is Dexon Wang, is an electrical engineer in the optimization and control group at P&L, and he received his PhD with a focus in communications from Colorado State University in 2019, and his research interests includes power system resilience, energy storage systems, and transactive control, with special focus on communications dependent grid functions, co-simulations, and optimizations. And last but not least, Dr. Sanjeev Pannala is working as a postdoctoral research associate in the Energy Systems Innovation Center at WSU Pullman. His research interests include distribution system resiliency, event detection algorithms, ADMS, and microgrids. He worked on the India-UK HEAPD project to earn his PhD at IIT Roorkee, and later he joined as a research associate for the UI Assist project at before coming to WSU. He also received a postdoctoral POSOCO Power System Award in 2020 for contributions for his PhD. So with that, I'm going to stop sharing, hopefully, and turn it over to our 4 presenters.
Noel, thank you very much for that introduction. That's wonderful. Dexter, can you please share the screen and also help to operate the slides? Again, thank you, Noel, again, for inviting us, the team, to give this webinar. I think this is really a good opportunity for me to show off my WSU shirt. Also, thank you, Noel, again for the gift. I also appreciate the introduction of me. You mentioned the young engineer item. I really wish the word young still applies, but I'm glad that we have a lot of young engineers and researchers on our team, and you'll hear from them today. So basically, what we do is we're doing teamwork today. I will be the one opening the talk, and Anurag will be the closing part. In between, the real meat will be presented by Dexter and Sanjeev. So we'll show you really we're a great team working on this project. With that said, if you move to the next slide, our team is actually much larger than just the 4 of us. You can see over the last couple of years, there's a lot of people being involved in this project, including power engineers, including a computer scientist, software developer. Any questions, someone? Okay. So we worked really well together across the different domains. That's really the important thing we need for this project, because we are aiming for the multi-domain power grid analytics. We go to the next slide. So what we'll do is, again, I will give you a quick overview, and then Dexter and Sanjeev will give you the update on how we actually developing GridSandbox with some use cases, and Anurag will close with the future work. Next slide, please. Next again. So when we talk about the power grid analytics, that of course is a lot of things being involved. But one important thing I want to bring out for today's conversation is the modeling simulation for the power grid. As we know, the power grid really is heavily rely on modeling simulation, because you cannot really do physical experiment on the grid itself, and you cannot even have an actual mock-up grid, physical grid, to do experiment in this larger scale. So modeling simulation is really the way we can understand such a complex systems. And then, so the way we're doing that in the past is we just build a model based on the understanding of the grid physical behaviors, starting from one power line from New York, maybe 120 years ago. And then as the grid is growing with more and more lines and the power plants and substations, we just add more those elements to the model. So the model gets larger and larger over time. So that is the way we've been doing the modeling simulation for the grid. However, as we're moving into the new era for the grid, it's the old approaches will no longer work. The new challenges are the grid itself is no longer just a grid alone. Grid become more and more connected to other systems, and there's a lot of more interdependency among the systems we have to consider. So here, just a picture to indicate the grid has its own complexity from transmission to distribution. Used to be, 2 maybe clear division line between the 2, but now it's no longer the case. Plus, communication as being a really central part of the grid planning and operation. With the bigger push for electrification and decarbonization, buildings, the transportation, the vehicles being put onto the grid and become active participants. we can no longer ignore them when we study the grid because they are all affected. Plus, gas pipelines and so on also be important. As you all probably know, last winter, Texas has a big issue with the gas outage and which caused the power outage for the power grid. And then the interdependence is really a huge thing to be studied. Even DOE put a huge effort along these lines. It's called the NAM, North American Energy Resilience Model, to look at this interdependency and build a lot of tools for that. So with that said, the old approach by adding more component models to the bigger databases no longer work because you cannot add all the vehicles to the grid model, all the buildings to the grid model, and then solve the huge equation. That's just impractical to do that. So the approach would be you keep each domain have their own models and their own tools, and then work the things along the interface, which is a code simulation. That's also an important thing being worked on by DOE as a GMLC project called Helix. I was leading at the beginning. Now Jason Fuller is leading the Helix Plus, the new project. So that's a huge effort as well. Now with that, assuming the code simulation is all successful and then be able to run every simulation we want to run, but still a remaining question is you have a grid model, you have a gas pipeline model, buildings model, communications model, EV model, transportation system model, and then bring them all together. Even you can solve the code simulation challenge, but still how to construct such a complex simulation and still become a bigger challenge. The analogy I'm using here is, like building the Lego construct. You have a lot of pieces. Each Lego piece has its own unique features. Fit them together. It takes a lot of time. Just like my 7-year-old son is doing that all day long, and it takes a lot of time, to do those constructs. So what we're trying to do is can we automate that construction of your simulation environment, and then you as a user don't have to learn everything yourself. You may be good expert, but you may not be knowing enough about communication or transportation or gas pipeline systems, and take a lot of time for you to learn to be able to do that. So we hope we can overcome that barrier for more efficient multi-domain simulation and analytics for the power grid. So that's the purpose of GridSandbox. It's built on top of all the work we've been doing, and then trying to have a new approach for grid modeling simulation moving forward. And next slide, please. And this is just one slide to show how complex the power grid becomes over time. This is architecture pictures from our colleague, Jeff Taft. He's leading a significant architectural role, a project for DOE. I'm not intending to show the details. The purpose is to have this picture crowded on one slide to show you how complex they are and how many details you have to look into. So that's the complexity we're dealing with. And if you go next slide, and we'll really look at how to effectively and efficiently model and simulate and analyze this energy ecosystem, which has a grid in it, but also many other pieces, other domains. And the GridSandbox, it's really like the name says, it's a sandbox for you to play, and you'll be able to construct things based on your requirements. And then Sandbox will have the function to build that simulation for you and make the connections, which includes hardware, software, models. More important, there's a portal on the web. You can interact with Sandbox, and you don't have to go into the details of the backend. You need to send your high-level requirements for the Sandbox to build the simulation for you. So that's really the next slide. If you see the architecture of this Sandbox, there's a lot of pieces here. Really, the gray pieces are already existing, and we are leveraging, including Helix, including other simulators here. And then the red pieces is really what we're trying to build, and we're building a lot of them already. The web portal is the one have a direct interface with users, and then the backend has this data processing, data communication middleware to help to build the simulation for you. So that is the case we're building here, and also the tools we hope to help the users. It's being applied to many cases within our project, and also I just learned today there's a NASP, the North American Synchrophasor Initiative, also look at how to simulate the new communication architecture for the phasor network, and then there's a project being approved, and they're going to use Sandbox for a big piece of that. So that's again the usefulness of these tools. So with that said, I'm going to transition to Dexing to show you more details of how we actually develop Sandbox and how we interface with the users and what are the kind of ways the users may be able to leverage this capability. And then follow that, it will be Sanjeev give you use cases, and again, Anurag will close the whole presentation. So Dexing, can you please take away?
Yeah, sure. Thank you, Henry. Yeah, so we built the GridSandbox from a web-based approach, and it's a cloud-ready architecture and implementation. So every component of the GridSandbox is packaged in a Docker container, and they can be deployed to the cloud right away. And so first, I'm going to show a video that demos how the GridSandbox facilitates every step of the workflow when doing grid-related simulations and studies. And so first, you're on this dashboard page, and what you can create a new project or revisit an existing project that you've done before. And in this interface, you can inspect the models in the communication network or the transmission network, and you can inspect the nodes, the edges, and the applications installed on each node. And you can change or add applications to it, and also the parameters for each application can also be configured through this web interface. And so in this case, we're configuring this PDC app, and so obviously we can also delete an app or even change the topology of the communication network. And so we can move a node to a different location, etc. And once we hit the run button, it is the project is built, the request is sent to the server, and it's built and run on the backend server. Yeah. So, and after, in addition to that demo, what the demo has shown, we've also developed the user authentication or sign-in page for the UI part, and then we improved the usability of the communication network model configuration tab of that UI. We added the search and the zooming in and zooming out functions to help, which are very critical when dealing with large models. And we also added the configuration panel tab for the control agents, which will be used in the peer-to-peer transactive energy agent use case, and also or other similar studies. And so next, I'm going to go over the first use case that we have developed to showcase the capability of the GridSandbox. So this use case is called Nasminet. So it's designed to the main focus of this use case is on the communication modeling. And Henry has mentioned that the communication network has become an integral part of the power system, and it has a lot of impact on the power system. So we need a way to evaluate how much does it affect, and how can we improve that. And so this use case is we want to compare the performance of the original Nasminet and the Nasminet 2.0 in the context of wide area control. And we're using PMU measurements for wide area power system stabilizer control. And the main this shows the main difference between the original Nasminet, or we can call it a Nasminet 1.0, and the proposed new Nasminet or Nasminet 2.0. And the difference we want to focus in this use case is the way the network architecture or the structure of the network. So in the original Nasminet, we have a lot of PDC at the begin sitting in the middle of the network. So the PMUs first send their measurement to the PDCs, and then PDCs may send their measurement, the concentrated data frames to a higher level PDC, and then there is even a super PDC. This is what happens in practice, and people has been this PDC stacking is happening in the industry, and this causes problem that potentially causes like a very high latency, and that's additional latency on top of the network latency themselves. And so the part of the motivation for Nasminet 2.0 is to reduce or eliminate PDC stacking. So we want to put PDC as a function at the edge of the network instead of a box in the middle of the network. So that's the main difference we want to demo for this use case. And so in this use case, it involves some component level modeling. We modeled the PMU, the PDC, and the synchrophasor sync app, and these are all in the communication system, the NS3 simulator, and also involves a network level modeling, which involves the development of the network model themselves, the topology of the network, and also build some also assign the devices or applications in at various nodes in the model, in the network. And this slide shows an example data flow that will be used in the co-simulation. So in the physical subsystem, or which is simulated by GridPack, there are PMUs. Sorry, these are two PMUs. They make measurements, and the measurements are published to Helix. And those, and on the cyber side, the NS3 simulator subscribes to those publications and encapsulate those raw measurements. So this frequency, for example, according to the C37118 synchrophasor protocol, and then also further encapsulate them into UDP protocol, IP, etc. And these are done in both PMUs, and then sent over the network to the receiver, and the package is decapsulated, and the raw measurement is obtained there. And then we do the processing at this at the receiver, and they are sent back to the consumer of the data on the physical subsystem. So in the component level modeling, we first modeled the PMU application, which sends a double value along with the PMU IDs and timestamp over the communication network according to that C37.118 protocol standard. So it is compliant with that standard. And another part is the PDC modeling. So this is probably the most or one of the most sophisticated application we've modeled in NS3. It handles it receives the packets that sent from the PMUs, and it adds those to a frame buffer, and those measurements are aligned in the frame buffer. And then once everything is received, every expected PMU measurement are received, or a timeout window has expired, then this concentrated or consolidated phasor measurement data frame is sent out to the destination of the PDC, and that can be a super PDC or an end user application. Yeah, and it also is compliant with the synchrophasor protocol. And another key piece of this the component level modeling is the synchrophasor sync app, and its purpose is to perform the data concentration function at the consuming end. So, for example, the wide area controller, and publishes that reading from the PMU measurements to Helix, so that can be consumed by the physical simulators. Excuse me. And the parameters related to this application are the Helix publication pointers, which points to the Helix publication object in the software, and a publication key, which designates the Helix publication, the key of the Helix publication we want to publish the result to. And this expected stream IDs are the IDs of the expected incoming streams, which can be a PMU ID from if the stream is from a PMU, or the ID of the PDC if it's from a PDC. And the expected PMU IDs are it stores all the expected. So that's different from the stream IDs, that all these are PMU IDs, and these are the measurement that the consumer of this application is interested in. So, for example, the wide area control application, they at this point, they may receive data frames consisting of many different measurements from many PMUs, but they may only interested in 2 of them. So this is to specify that. And the historian app is also developed for debugging purpose and future reference for logging. Yeah, and also we this is the main part of what we have done for the communication modeling. We have developed a automated communication network modeling function or capability, where we can specify the node and the channels. Excuse me. We can specify the nodes and channels in a YAML file, and which will be which is the what's happening behind the scene at the web UI. So when you're clicking the mouse, clicking on the adding node or changing the topology on the web UI. There is a YAML or JSON configuration built behind the scene, and that is eventually sent to the NS3 simulator, and NS3 will be able to parse those configurations and build the network model automatically. And this video shows how we're gonna build a Nasminet, or how we can use the GridSandbox UI to do this kind of simulation. So first we'll we add a PMU at this generation bus, and we can add a control center node that we can add a control center node and add the PDC application on that node, and set the expected stream IDs from those two PMUs. And then we add the PMUs and the synchrophasor sync app at the consuming end. And then so once everything is set up, the simulation is run, and we can do something similar but different, but also different in the Nasminet 2 project. We add the PMUs and the synchrophasor app, but this time there is no PDC sitting at the control center, so there is no PDC stacking happening. And we can run this simulation, and once it finishes, we can inspect the simulation log and the results that's plotted in the output page. And these results can also be exported. Both the input and the output can be exported by clicking on that export data button, and that can be used for further analysis and plotting, or more custom plotting offline. Yeah. And this figure is actually plotted with the data that's exported from the GridSandbox. And we can see that in Nasminet 1, because of the PDC stacking, the generative speed oscillates and becomes unstable. And the Nasminet 2, in the Nasminet 2 case, it's because of that lack of that additional latency caused by PDC stacking. There is no the system is the oscillations is well damped, and the system go back to a stable condition. And on top of these end use results, we also can inspect the network communication network measure results that are the delays in the average delays on each of these communication links. And we can see also that the delay themselves are indeed smaller in the Nasminet 2.0 case. Yeah, next I will transition to Sanjeev to go over the distribution level use case.
Yeah, thank you, Dixon. So now actually we are transitioning to the P2P market use case. So just I'll brief about what is the use of the P2P market. The P2P market is basically give you a online market platform where like a consumer with the generation, local distributed generators like a solar PV or a battery energy storage systems, and they can participate in a local market, and then they can sell their energy to the neighboring peers or the local within the local community consumers. So without having any negotiator or intermediary. So that is like a P2P market mechanism, how it works in general. And there are like a very few business models exist in North America as well as in Europe. but there's still the research is going around the peer-to-peer market. And what is the best, actually the advantage of the peer-to-peer market is it will reduce the network congestion because you're utilizing the resources locally or within the community where the prosumer or the distributed energy generators are there, and then they're selling their electricity or the generation to the neighborhoods or the nearby communities. So you're not actually transmitting, or you're not sending or dispatching the power to the central operator, so where you're reducing the overall burden on the distribution system side or the operator side. And it also give you a benefit of effective utilizing the local resources and the reducing the losses, and also it can give an option to participate for the ancillary services if needed in situations where the generation is not or the supply is not sufficient from the upstream of the sub transmission level. So, and further it also encourages a more deployment of the local energy resources. So, and that is like a major usages if you see the current business models around it, around the world. Now coming to the grid sandbox, I mean the how actually we are making use of the P2P market here is this is the overall framework that we envision from the grid sandbox project. So it has like different use cases like Dexin and Henry talked about, like one is the Nasminet comparison from the data analytics side, transmission or the distribution side, and then a PMU PDC synchrophasor sync app. And so those are one of the use cases. And another use case what we are looking into is the transactive or the P2P market. It involves with the distribution, communication, and the market. So can you go to next slide, please? Yeah. So this is the distribution, communication plus market that we are actually focusing for the P2P market use cases. So here actually we are taking the GridLab-D, a simulator where we can simulate a typical distribution model right now. So we are just shown the IEEE 13 node feeder model, and with the distributed solar PV units across different nodes that spread. And then we are we are considering those as like a prosumers, like with the load and the local PV generation. And then there are like other load nodes which can take the advantage of the energy that is available within that community or within that feeder level, or even it is maybe a community level. So that is the GridLab-D where we are using for simulation of the node feeder model. And then the Helix will be taking the co-simulation engine we are using to connect with the corresponding or the associated communication network that we built in the NS3 network simulator 3. So it has the equivalent communication model of the network which can exchange the information from the physical to the communication side, where the control center can get the access to the actual information, can take the decision. So, and here the Helix will be giving us the database or the historian through which we can perform applications like a peer-to-peer market model or the distributed optimization or the transactive agent-based coordination. Can you just move to the next slide? Yep. And as a process of the communication network side, so we build the DNP3 app, I mean the protocol app. So DNP3 basically a distributed network protocol 3, which is typically used in a control center for communicating or for establishing a communication between the RTUs, remote terminal units, or the IEDs, and to the SCADA or the control center. So that is the general protocol we use it. So it comprises of the 3 layers. So in S3 we do not have a direct DNP3 protocol. So it is built in a part of this project, and that will be, we are making use that communication network for passing the information between the communication nodes of the corresponding physical nodes for the peer-to-peer market. And the DNP3 can be transmitted over the serial bus, or the transmit can be a TCP/IP. And so this is like a typical architecture, if you can say it. If you just move to the next slide. Yeah. So here, this is the packet structure. So, oh, sorry. Okay, can you go back to the last slide? Yeah. So this is the data structure, the DNP3 data structure, and then the corresponding function codes and how they actually bitwise the explanation is given. And then so I'm just directly jumping to the application. Next slide, please. So here, so how we are utilizing the DNP3. So in NS3, so we will be using the DNP3 app to come pass the actual information between the each node that lying in NS3, and then these Python agents are basically the agents which can act as like a distributed agent for implementing the peer-to-peer market optimization algorithm. So these are actually the Python agents, and it has the direct information. It is a kind of a combination of message and the value that is coming from the federates from the Helix engine. So these are the two different federates. One is the NS3 federate, and this is the P2P market federate. And so the market will be getting the actual load and the generation and the measured values, and then the bidding prices from the each the prosumer or the participating distributed energy generator. Next slide, please. So this is the overall architecture so that currently we are working on. So we have like three federates. The one federate covers the GridLabD, that is simulating the typical distribution feeder model and it has prosumers, consumers, and load nodes. So those so in that, and then the corresponding communication network were actually implemented in the communication federate. So the GridLabD federate is basically a value federate because it just exchanges the value of the information, like what is the generation and what is the load value, and that is in terms of the double in format, type format. And then, but coming to the communication side, because the communication generally receives the values from the GridLabD federate, and then also it exchanges the messages, I mean the which non unitless values or the unitless information to the market, where it can give the bidding price from the particular prosumer 1 or the prosumer 2, like agent 1 and agent 2. So the bidding and clearing mechanism is actually coming from the distributed optimization, P2P distributed optimization. So the other federates, the intermediate federates, is from the P2P control agent or the market agent. So this is again a combination. It's a combination federate which has both value as well as the message, because it has to give the cleared price and then set point corresponding to the prosumer, so how much it has to dispatch from a particular prosumer. And here we are considering the three different distributed coordination or the optimization algorithms that is given with the references. And currently this work is in progress, and hopefully we'll finish it soon, and then we'll give the more results, interesting results from this. Then I'll hand over to Dr. Anurag for concluding the oral presentation.
Thanks, Sanjeev. So a lot of work has been done, and as Henry said, that as we evolve towards more DRs and more active distribution system and then more sensor and transmission grid, our ability to simulate also need to evolve. And GridSandbox is one of the effort towards that. So it does allow you to explore, develop, and validate your possible solution to in a more user-friendly web interface. And the idea was that anything that we can simulate, assemble different set of tools that already exist, and integrate it in a better way, so it will take less time for you to do the simulation. And GridSandbox specifically works with Gauss and Helix, and does offer a flexible and scalable workflow. And you just you looked at the two different examples for transactive energy and synchrophasor. Again, as we continue this work, we are hoping to complete this transmission and distribution and communication and market interface, building on and leveraging on that what we already have, and offer a platform to do a large-scale interdependency of different, this transmission, distribution, communication kind of domain simulation. So the two examples we already talked about, transmission synchrophasor system, and the one in progress is for transactive energy, peer-to-peer. And to continue our future work, we will be, basically focusing on more visualization and making it more automated, such as editing of communication network model configuration through the web portal, and also offer more flexibility and offer more interface, such as DNP3 using NS3 interface with the distribution system as we continue. One thing that, even though there are thousands of cases possible moving into future, but data analytics will be one immediate one that will be possible once we have a complete set of interdependent domain model and generate set of data that can be used for different data analytics kind of or machine learning kind of application too. Okay, well, I think if there is any question, we can all answer.
Thank you, Anurag, Daxin, and Sanjeev. Noel, I guess I will give this back to you to see if any questions.
Yeah, there's one question in the chat. If a wide area monitor based controller is designed and needs to be tested on the Sandbox, how can a user achieve that?
Yeah, that's Chihuahua. This is a great question. This is exactly one of the kind of things that we are envisioning to help to make it easier for people to do things like that. Let me give you my quick answer, and then others on the team, please add more to it. So I think that 2 steps we would do. One step is the user, him or herself, need to do is integrate the controller into the physical, say, power system model first. That's a part is within the power system domain, so that's need to be in place. Now the Grid Sandbox can help in the case to deal with the communication side. As long as you gave the interface parameters, like which node from the power grid talking to which node in the communication, then the Sandbox can help to build this simulation platform for you, and you can use that simulation then to assess and measure the performance of this controller. So that would be the kind of 2-step process. Anurag, Daxin, Sanjeev, anything you want to add?
Yeah, thanks, Annie. I think you captured it well. And one other point that I would like to mention, that you saw that PMU and PDC does have a following IEEE standards. So, and with communication network model, we can even reduce the delays and all those kind of simulation, which will impact the performance of or validate the performance of controller wide area. So all these things are possibly done.
Okay, Dr. Manny has a question. Oh, sorry.
Yeah.
Jackson, did you want to say something to Anurag?
Yeah, I just want to add one more point. For the wide area PSS controller, so in this demo, we just showed with a generic PSS controller, and the main focus is to investigate how does the communication network, different configuration in the network will affect the performance of that PSS control. And but in the future, we can add a custom PSS controller and expose some of the parameters or even algorithms to the user, so that you can experiment with different custom PSS controller configurations. Yeah.
Okay, sorry, Dr. Manny.
Thank you, Dr. Schultz. I have a question on slide 23 on the simulation between Nasminet 1 and Nasminet 2. I wanted to understand, I apologize, I joined the meeting a little late, so I may have missed something that you explained already, but I am curious, what is the difference between the blue plot, which is showing an unstable trajectory, versus the red plot, which is showing a stable performance of the system?
Yes, so
Yeah.
the difference is, oh, Henry, go ahead.
Go ahead. No, go ahead, Anurag.
So difference is mainly because of delay.
Okay, yeah, that's what I understood. So if you go to the slide 23, the difference in the delay between the two plots appears to be a few milliseconds, if I understand it correct, because one is showing 7.5 something and the other one is 5.92, for instance. So that would imply the difference is 1.5 milliseconds. And I'm, I'm puzzled that such a small difference in delay would lead to instability, because few milliseconds, or in this case, less than 2 milliseconds, should translate into a few degrees when we think about stabilizing control in terms of either a phase lead or phase lag or whatever is the stabilizer that you are working with. And that should not make the trajectory to change from a stable response to an unstable response unless the controller was designed near the limit, which is not how it is done in reality. Or so I'm puzzled how such a small millisecond change would destabilize the control. That doesn't seem realistic. Henry,
I think
you are the control person. I'm putting you on the spot.
Sure. Dexon, go ahead. I guess Dexon was trying to say something first.
Yeah, let me first clarify something. I'm sorry if this causes some confusion, but this table, this slide is just to show the different kinds of results that we can get from the GridSandbox. And this table, the communication delays that's shown in this table, and the results they're actually from different networks and different topologies. So yeah, you pointed right. So the delays, the actual delays that caused this kind of behavior in the Nasminet 1 is probably much larger than just a few milliseconds.
Okay, can you give a ballpark figure? How much was the difference between these two?
It's been a long time since this.
That's okay.
Yeah,
we can chat offline. Thank you for the clarification.
It's probably in the ballpark of maybe tens or even 100, something like that.
That is more believable.
I think it's in the order of 10 milliseconds range. Think about PDC, right? Your PDC is waiting for the PMU measurement to come together, and then so the delay caused by PDC is like how it's in that PMU sampling rate. If you one PMU measurement coming at the beginning of time window, another one come at the end of time window, and then PDC have to wait for all the PMUs to come and then be able to form the new packet. So you 30 samples per second. That's really like a 15 or 30 millisecond range. So that's kind of the range.
That shouldn't make a difference, Henry, in a good design. So if it is hundreds of milliseconds, then it's possible that it changes the response of the system. But if it's in the milliseconds or even tens of milliseconds, it should not affect because the swing is 0.17. It looks like each one is about 1.7 second period. So that looks like around 0.6 hertz. So 1.7, and even if we are saying 30, 40 milliseconds, that's still a small portion of the swing. So in terms of degrees, that's really not very much. And so, you can translate the milliseconds or whatever is the time lag into the compensation angle in terms of the phase, and that will give you a good indication whether the lag is going to matter in terms of changing the response. I just wanted to point out that this is all standard linear system theory, and so I'm sure you are very familiar with it. I was just puzzled by the table, but you have explained it nicely. Thank you.
Yeah, Manny, we'll get back to you with the specific numbers. Yes, definitely the leading lag time constants deciding how sensitive the controller is to the time delay. I just want to add one more thing as it takes an expert to ask this question. Thank you.
Yeah, and I just want to provide more detail that definitely it was not well designed in the sense that we did not focus on that part, and it is 39 bus system, and we simulated a fault for like at 1 second, and then in one cases it was when why do PSS work and took action, and another one does not, right? Because it was not well designed to take a right action at the right time with the delay.
Thank you. Thank you.
Okay, well, I don't think I see any more hands up, or I don't see any more questions in the chat. So last chance for anybody. All right, well, thank you very much to our 4 speakers. We appreciate this update and sharing about this collaboration, and it's a great example of some of our work that we've been doing together between Pannala and WSU in this space. So we appreciate everybody attending, and next month we'll have a webinar on our UI Assist project that's a collaboration between Pannala and WSU. So thanks everybody, and have a great day.
Thank you, Noel.
Thank you.
Thank you.
Bye-bye.